In this next video in our pipe flow series, we are going to discuss the fully developed laminar flow velocity distribution, and I'll also touch on the fully developed turbulent velocity distribution. Let's start with some terminology so that we're all on the same page. The first term I want to discuss is the boundary layer. And the boundary layer is a layer of fluid in the immediate vicinity of a boundary surface where the effects of viscosity are significant. And just to refresh your memory, what is viscosity? Viscosity is a measure of a fluid's resistance to the gradual deformation by shear stress, as opposed to normal stress, due to molecular attraction or friction between neighboring particles of the fluid moving at different velocities. So think of it as a resistance to flow. Something like molasses has a higher viscosity than water that has a higher viscosity than air. The no-slip condition. The no-slip condition is important when we're determining the velocity profile and understanding boundary layers, and the no-slip condition states that when a fluid with a uniform velocity enters a stationary pipe, the velocity of the fluid at the pipe wall goes to zero. So it means there are particles of the fluid that stop at the wall, and they stay there, and they cling onto that wall, and then subsequently they grab onto expanding outward, or I should say inward, towards the center of the pipe. Propagating inward, they're grabbing onto those other molecules and trying to slow them down. That's how we get our velocity profile. I remember when I first learned this, I thought, I don't believe it. That's a math trick. There could be no way that there is fluid at the pipe surface that's not moving. So let me show you a quick video within the video of the no-slip condition. So here you have water moving from right to left inside a closed conduit, and they've injected a dye via a tube. So you can see that away from the walls, the surface of the bottom, the velocity of the fluid is carrying that dye away. But at the bottom, where it's touching the bottom, the velocity is zero, and the dye is literally resting on the bottom. And just to prove to you that it didn't stay in the bottom and dye it, they can brush it around and mix that fluid up and get rid of that fluid. So you can see that there actually is a no-slip condition in which at the surface interaction with the fluid, the velocity is zero. And that's going to dictate our velocity profile for any velocity, especially for a closed pipe. And finally, let's talk about fully developed flow. Fully developed flow is flow that once the boundary layers merge, there is no further change in the velocity profile in the direction of flow, and then I can assume no matter where I'm at along the pipe, the velocity profile is going to be the same. And so it takes a while for that to happen. You have to have your boundary layers merge. So let's discuss that. Let's explore that a little bit further. So the laminar flow velocity profile. So this is a figure 9.2 from your book, and I'm gonna break it down piece by piece. So I have a flow, and I have a uniformly distributed velocity of a fluid entering that pipe, and I've got my coordinate axes on the right-hand side, where x is the longitudinal axis of the pipe, centered in the center of the pipe, the circular pipe, and I have the radial direction acting outward in 360 degrees outward from my longitudinal centroidal axis of the pipe. So once that fluid first enters the pipe, because the fluid, and realize this is really three-dimensional. This would be circular, this profile. We're just looking at a cross-section cut. As it enters, that fluid that's in immediate contact with the walls all the way around immediately stops. It grabs on, it stops, and it propagates its way out. So as that viscosity of the fluid, depending on the velocity of the fluid, would dictate the shape of this profile, how dramatic the shape of the profile is, and how big the boundary layer is. It subsequently affects other particles or molecules of the fluid that are getting closer and closer, or further and further away from the wall, or closer and closer to the center of the pipe, which alters their velocities. Now, conservation of mass tells me that what goes in has to go out. And so because the fluid closer to the walls is being slowed down, the fluid in the center has to speed up, so they have a much faster velocity profile. So what the velocity is at anywhere in my fluid, if I want to know the velocity here, the velocity here, the velocity here, when I first enter the pipe, it's a function of both the x direction and the radial direction. Now let's move a little bit further down the pipe, and this dotted line here is an indicator of what's called the boundary layer, and this del is indicating the height of the boundary layer. And you can see as I move further and further down the pipe, this is obviously exaggerated for visual purposes. In a real pipe, this would be very, very small and would take a long time for this to happen. But 360 degrees around, all the way around, I'm building up a boundary layer. The velocity in the middle has to continue to increase due to conservation of mass to make up for these particles that are moving slower, until eventually I reach a point where the boundary layers converge. They merge together in the center. And so up until this point, like I said, the velocity is a function of both the x and the radial directions. This is what we call developing flow, or the growth of the boundary layer, this region. And this is obviously shortened, and I'll talk to you in a moment how to calculate this. Once those boundary layers merge, then there's no other effects of the boundary layer. There's no changing effects. It's not growing anymore. It's merged in the center. I get a parabolic velocity distribution, where again the center is moving faster than the sides, or those closest to the wall, to compensate, because it's essentially creating its own venturi. But now that it's set and it's established, that velocity profile doesn't change. And that's what we call fully developed flow. Once the boundary layer has merged, the velocity is now only a function of the radial direction. It doesn't matter if I'm right here in the pipe, or if I'm 6 inches down the pipe, or 10 feet down the pipe. Once I have merged my boundary layers and I'm fully developed flow, the velocity is only a function of the radial direction. So I want to know what the velocity is here at the center, or expounding outward radially. It's obviously going to be different as a function of the radius, but it doesn't change. This profile looks exactly the same as it moves down the pipe. Now, the distance it takes for the boundary layers to merge is what's called the hydrodynamic entrance length. And that's something good to know, because we're going to develop equations later on for the mean velocity, which is what's annotated here as v sub m, the mean velocity, the average velocity of this parabolic distribution. In order to use those equations, I have to make sure that I'm in the fully developed flow region, which means I have to first compute the hydrodynamic entrance length of my pipe. So the hydrodynamic entrance length, or L subscript E comma H for entrance length hydrodynamic, and this is done experimentally, is approximately equal to 0.06 times the diameter of the pipe times the Reynolds number that you learned in a previous video. And that's for laminar flow, and that's equation 9.6 in your textbook. Now this is different for turbulent flow. For turbulent flow, the hydrodynamic entrance length is approximately 4.4 times the diameter times the Reynolds number to the 1/6 power, or the 6th root of the Reynolds number times 4.4 times diameter. That's equation 9.7. So let's delve into this, but let's first look at what a turbulent velocity profile looks like and compare that. So a turbulent velocity profile, I've got all that mixing and that disordered flow. As it enters the pipe, let's compare that to our laminar flow velocity profile. So in the light gray in the background, you can see the laminar velocity profile. We've overlaid on top of that a turbulent profile, and you can see that the turbulent profile isn't nearly as extended, as nearly as parabolic. It's very close to a uniform distribution. You wonder, with all that tumbling and stuff, why is that? Well, first you have a viscous sublayer. You still have the no-slip condition, where the water, or the fluid I should say, that's interacting with the pipe walls has the viscous forces dominating, and you have a no-slip condition, similar to laminar flow. As I move outward from there, however, I get what's called the overlap layer, and that's where inertial forces and viscous forces essentially equal out, and there really is no one force that is dominant. Once I get slightly beyond that, I get to the outer layer, and that's where the inertial forces dominate. It starts tumbling, it starts mixing, and it results in, really, if I look at the mean, a nearly uniform velocity profile. So let's go back to this hydrodynamic entrance length, and let's talk about that. If you're just looking just purely at the math and you're just glossing over it, you'd say, well, Reynolds numbers for laminar flow are 2,000, and Reynolds numbers for turbulent flow are greater than 10,000. And the turbulent flow is multiplied by 4.4, laminar flow is multiplied by 0.06. So turbulent flow must take longer to develop, and that is actually not true. Turbulent flow will develop much quicker. So let's take a look at the math, and let's just put some arbitrary numbers in your head. If I have a Reynolds number of, let's say, 2,000, that my maximum extent of laminar flow times 0.06 times, let's say, a diameter of 1 inch, that's still a relatively large number. If I compare that to the same diameter pipe, multiply by 4.4, if I have a Reynolds number, even if it's 10 to the 5th or 10 to the 6th, I'm going to get a Reynolds number, if I take the 6th root of that, of 10, 12, something much, much smaller, depending on the values of it. Multiplied by 4.4 is still much smaller than something 1,000 multiplied by 0.06. So if you're comparing a laminar flow versus turbulent flow and wanting to see which one develops first, you'd have to have a really, really, really low laminar flow velocity to get a really, really low Reynolds number for the same fluid. that it's almost not even moving, to have a hydrodynamic entrance length that's even close to being as short as that for turbulent flow. And think about that. Go back to what I said about this is an exaggerated profile of the boundary layer. In reality, it's microscopic, and it takes a long, at the beginning, it's very, very small, this the height of the boundary layer. It takes a long time for these boundary layers to fully converge in order to get your fully developed profile. So it takes a much longer length of pipe in laminar flow to get this fully developed flow, with which you can use the equations that we'll derive in another video. Whereas turbulent flow, it's tumbling around, it's very disordered, but it does so relatively quickly for a relatively shorter length of pipe. So just some things to consider and chew on. That concludes the video.